Clair Patterson, a young geochemist at the University of Chicago, struggles to date the Earth using lead isotopes and zircon crystals, but his data is ruined by mysterious contamination. With George Tilton, he adapts uranium-lead dating methods, aiming to calculate Earth's age from primordial lead composition. Tilton measures uranium in zircons, Patterson analyzes lead. The zircon should contain only uranium-derived lead, but Patterson consistently finds excess lead. The known age of the rock matches Tilton's data, yet Patterson's results are skewed, suggesting contamination from an unknown source. For 6 years, they publish methods for zircon dating, but fail to determine Earth's age. Harrison Brown secures funding and a new mass spectrometer at Caltech. In 1953, Patterson and Brown moved to Pasadena, where Patterson is authorized to build a lab from scratch. Determined to eliminate contamination, Patterson creates one of the first clean rooms. He acid cleans all tools, distills chemicals, and seals off air sources. His extreme precautions are dismissed by peers, but he insists that purity is essential for accurate isotopic measurements. Patterson analyzes iron meteorite lead from the Canyon Diablo meteorite. Using a mass spectrometer at Argonne National Laboratory, he isolates lead isotopes free from terrestrial contamination. The data reveals a consistent isotopic signature that reflects the solar system's primordial composition. In 1956, he publishes Age of Meteorites and the Earth, calculating Earth's age at 4.55 billion years with a margin of error of 70 million years. This figure supersedes the widely accepted 3.3 billion year estimate and becomes the standard for decades to come. Patterson's clean lab allows him to isolate microgram quantities of lead from ocean sediments. By comparing Atlantic and Pacific samples, he finds anthropogenic lead exceeds natural inputs by more than 100 times, indicating a severe imbalance in Earth's geochemical cycle. He observes that surface ocean waters contain up to 20 times more lead than deep waters, using barium as a comparison. This contradicts the assumption that human activity has only doubled lead levels, revealing a far greater impact from industrial sources. Patterson turns to ice cores from Camp Century in Greenland, collected in 1964, and samples from Antarctica in 1965. These layers preserve atmospheric lead levels over time, showing a sharp rise coinciding with the introduction of tetraethyl lead in gasoline. The ice core data reveals that lead concentrations began increasing rapidly after the 1920s. This timeline matches the rollout of leaded gasoline, identifying it as the primary source of contamination that had plagued his earlier experiments. Patterson realizes that the contamination he once dismissed as lab error is real and global. Industrial lead has infiltrated the atmosphere, oceans, and human bodies. He shifts his focus from geochronology to public health, dedicating his career to exposing the dangers of lead pollution. In 1965, he publishes Contaminated and Natural Lead Environments of Man, arguing that normal lead levels are not natural but typical of industrial contamination. He insists that common exposure does not imply safety, challenging long-standing assumptions. Robert A. Kehoe, chief medical advisor to the Eiffel Corporation, has long claimed that lead in humans is normal and harmless. His industry-funded research at the Kettering Laboratory supports the safety of tetraethyl lead, shaping regulatory policy for decades. Kehoe's position rests on the Kehoe rule. Unless harm is definitively proven, leaded gasoline should remain in use. This shifts the burden of proof to critics, allowing continued sales despite growing concerns about health effects. Patterson challenges Kehoe's methodology, noting that unexposed workers in lead plants still have elevated lead levels. He studies ancient Peruvian mummies and pelagic tuna, finding that pre-industrial humans had far lower lead concentrations. He shows that modern human bones contain 700 to 1200 times more lead than those from 1600 years ago, with no change in barium or calcium levels. This proves the increase is due to industrial lead, not natural variation. Patterson argues that evolutionary adaptation to lead is impossible within a few thousand years. On a Darwinian timescale, this is an instant insufficient for biological adaptation to a neurotoxin that had been absent from human physiology until recently. He tests canned fish and finds lead levels jump from 0.3 ng/kg in fresh fish to 1400 ng/kg in canned varieties. Official labs report only a rise to 700 ng/kg, but Patterson's clean lab reveals the true extent of contamination from lead solder. Despite his findings, Patterson is excluded from a 1971 National Research Council panel on atmospheric lead. The panel includes industry-linked scientists, but not the leading expert on environmental lead contamination. The Eiffel Corporation and lead industry lobby aggressively to maintain the status quo. They fund research, influence policy, and discredit independent scientists. Patterson faces professional isolation and loss of funding from neutral agencies like the Public Health Service. Patterson continues publishing and speaking, using ice core, bone, and ocean data to demonstrate the unnatural rise in lead. He insists that natural must refer to pre-industrial conditions, not current averages shaped by pollution. In 1973, He receives the J. Lawrence Smith Medal from the National Academy of Sciences. The recognition is rare for an environmental scientist, but it does not shift regulatory policy or industry practices. The U.S. mandates unleaded gasoline for new cars starting in 1975 to protect catalytic converters. This creates a market shift, but leaded gasoline remains available for older vehicles, slowing the decline in atmospheric lead. Patterson's data shows lead from gasoline is the dominant source of environmental contamination. He pushes for complete elimination, not partial reforms. His campaign gains traction as more scientists replicate his findings using clean lab techniques. In 1978, he is appointed to a National Research Council panel that acknowledges lead contamination. But some members call for more research before action. Patterson submits a 78-page minority report urging immediate controls. His report demands immediate action on leaded fuels, water systems, food containers, paints, and glazes. He argues that delay costs lives, especially among children whose developing brains are most vulnerable to neurotoxic effects. Lorna Laurie McCleary, Patterson's wife and fellow scientist, supports his work throughout. They met at Grinnell College, married in 1944, and raised 4 children while both pursuing scientific careers. She balances family life with her own research in infrared spectroscopy. Her quiet support enables Patterson to focus on his campaign, even as professional and political pressures mount. Patterson's activism draws attention from policymakers. His data is cited in congressional hearings, including those led by Senator Edmund Muskie, who pushes for clean air legislation. Kehoe testifies that his lab is the only source of reliable data on lead exposure. He claims widespread influence in shaping industrial and public hygiene standards, reinforcing the industry's control over the narrative. Patterson counters that Kehoe's normal levels come from contaminated populations. He insists that true baseline levels must come from pre-industrial samples, not modern workers or urban residents. He demonstrates that lead in canned food comes from soldered seams. Regulatory agencies had accepted industry-reported values, but Patterson's clean lab reveals far higher contamination, forcing recalls and reformulations. The EPA begins regulating lead in gasoline, but progress is slow. Industry resistance delays full phase-out. By 1986, the U.S. bans lead in standard automotive fuel, though aviation gasoline remains exempt. Patterson's work leads to a 90% drop in atmospheric lead over 2 decades. Blood lead levels in Americans fall by up to 80% by the late 1990s, validating his long-standing warnings. In 1980, he receives the V.M. Goldschmidt Award from the Geochemical Society. The honor recognizes his contributions to geochemistry, including both earth dating and environmental contamination studies. He continues teaching at Caltech, mentoring students in clean laboratory practices. His methods become standard in environmental geochemistry, ensuring future research avoids the contamination that once obscured the truth. In 1995, he is awarded the Tyler Prize for Environmental Achievement. It is one of the highest honors in environmental science, acknowledging his role in transforming public understanding of lead pollution. Patterson dies at home in Sea Ranch, California, on December 5, 1995, at age 73. His legacy endures through the global phase-out of leaded gasoline and the recognition of lead's neurotoxic effects. The Geochemical Society establishes the Clair C. Patterson Award in 1998, given annually to scientists who advance environmental geochemistry. It honors his commitment to scientific integrity and public health. Minor Planet 2005-11 is named in his honor, recognizing his contribution to understanding Earth's age. The celestial tribute reflects the scale of his scientific impact. Kehoe retires in 1965, the same year Patterson publishes his landmark paper. He becomes Professor Emeritus at the University of Cincinnati, where Kehoe Hall is named in his honor. His research, once considered authoritative, is later discredited. Historians note that industry funding shaped his conclusions, and the Kehoe Rule is seen as a template for delaying regulation through manufactured uncertainty. He dies in 1992 at age 99, outliving most of his contemporaries. His legacy is complex, a respected toxicologist whose work served corporate interests at the expense of public health. Leaded gasoline is finally banned in the U.S. on January 1, 1996. The phase-out takes decades, but Patterson's persistence ensures that lead no longer enters the atmosphere from cars. Global elimination follows. Algeria ends production in 2021, prompting the UN to declare the official end of leaded gasoline for cars. Aviation fuel remains a source, but road emissions are now zero. Patterson's campaign saves millions from lead exposure. Studies estimate that global IQ loss, crime rates, and economic damage drop significantly as lead levels fall in blood and environment. His use of ice cores, mummies, and ocean sediments provides irrefutable evidence. By comparing past and present, he proves that human activity, not nature, caused the lead crisis. He shows that lead in the food chain comes from industrial sources, not natural leaching. His analysis of canned fish exposes the role of lead solder, leading to regulatory changes in food packaging. His clean lab techniques become standard in environmental science. Researchers adopt his protocols to avoid contamination, ensuring that future studies reflect true background levels. The scientific community recognizes that normal does not mean safe. Patterson's distinction between typical and natural reshapes how public health interprets exposure data. Children benefit most from lead reduction. With lower exposure, developmental delays, learning disabilities, and behavioral issues decline across generations. Patterson's work influences the precautionary principle in environmental policy. When harm is plausible, action should precede absolute proof, reversing the burden of proof established by the Kehoe Rule. His legacy is not just in data, but in courage. He challenges powerful institutions, endures professional retaliation, and persists until science drives policy. The documentary of his life, The Clean Room, airs in 2014 as part of Cosmos, a space-time odyssey. It introduces his story to a new generation, highlighting his dual role as Earth's chronologist and protector. Historians credit him with one of the greatest public health victories of the 20th century. His quiet determination removes a silent toxin from the global environment. He proves that a single scientist, armed with rigor and ethics, can change the world, not through force, but through evidence, persistence, and an uncompromising commitment to truth.